Hi everyone, this is Fabio from the University of Bologna, and in this video I'll present our research project, NeRF-Supervised Deep Stereo. In this work, we tackle the deep stereo matching task. The limitations of acquiring costly ground truth depth information, the domain shift issues due to the transition from synthetic to real-world domains, the ineffectiveness of self-supervised techniques in challenging regions, and the difficulties in achieving optimal results across diverse datasets are crucial factors to consider. With the advent of recent neural rendering techniques, we introduce a novel stereo data generation process, eliminating the need for stereo cameras or active sensors. Using our training protocol on the proposed image dataset, we achieve strong generalization results on the main stereo benchmarks. We start with a single camera capturing images of a static scene. Then, we train a NeRF model on each scene and generate stereo pairs at arbitrary resolution and baseline with corresponding disparity maps and uncertainty. Using this information, we train any deep stereo network using a combination of photometric loss and the disparity loss on reliable points obtained from NeRF. Now, let's dive deeper into our methodology. In this work, we address the task of stereo matching, a long-standing topic in computer vision. It involves finding corresponding pixels in rectified image pairs to estimate disparities and thus infer depth. Deep learning revolutionized this field, with end-to-end deep networks outperforming traditional methods on existing benchmarks when trained with extensive data. The need for accurate labels is crucial for the success of depth estimation models, but also represents a significant limitation due to the requirement for additional expensive sensors like lidars. Synthetic data has emerged as a promising approach to address these weaknesses. However, the trained model's capabilities are compromised by the domain shift issue during real data testing. On the other hand, self-supervised learning paradigms offer the possibility to train on unlabeled stereo pairs. In spite of that, self-supervised losses struggle with ill-posed regions and often lack the accuracy achieved by means of the standard supervised training loss. To summarize, both approaches still have drawbacks that need to be addressed. Our idea is to use neural rendering solutions to create realistic images from different viewpoints. This helps us generate a wide range of high-quality stereo pairs with varying resolutions and baselines, enabling us to train deep stereo networks more effectively and achieve improved accuracy in depth estimation. By exploring a vast amount of training data, we can fully unleash the potential of deep stereo matching and achieve outstanding results. Summarizing, the key contributions of our paper can be outlined as follows. We propose a novel method for acquiring stereo training data using neural rendering, which allows us to generate realistic stereo pairs without relying on synthetic datasets, ground truth depth, or stereo cameras. Then, we introduce a NeRF-Supervised training protocol that leverages rendered image triplets and depth information to address challenging scenarios involving occlusions and fine details. Additionally, we provide an open-source stereo dataset specifically designed to train state-of-the-art stereo models using our protocol. Lastly, we achieve remarkable zero-shot generalization results on multiple real-world stereo datasets, highlighting the strength of our approach. In the next slides, we explore how to leverage NeRF to generate a potentially infinite number of stereo pairs. First, we take a picture of a static scene using a standard device like a mobile phone. Then, we employ CallMap to compute camera poses and internal camera parameters. This preparation step ensures accurate and reliable processing of the data to be employed for training NeRF. To this aim, we conducted an extensive data collection process, capturing a total of 270 high-resolution scenes in both indoor and outdoor environments. Each scene was captured to highlight specific objects of interest. More specifically, we acquired 100 images from various viewpoints to ensure full coverage. Moreover, in our acquisition protocol, we used a combination of 360 and front-facing views. Next, we fit an individual NeRF model for each scene. For this purpose, we use the collected images and decimated poses from CallMap. More specifically, we adopt the standard procedure to render color for a batch of rays shot from collected image positions and then optimize the underlying multilayer perceptron model. In our work, any NeRF-based approach can be employed to achieve this goal. After training a NeRF model for each scene, we generated thousands of binocular stereo pairs with variable spatial resolution and baseline. This process also involves extracting disparity maps and uncertainty, which serve as valuable training data for deep stereo networks. Additionally, we create a third image to the left of the reference frame for each stereo pair, resulting in a perfectly rectified stereo triplet. Data generated so far is then used to train stereo models through our NeRF-supervised training regime. As a first step, we generate a stereo triplet from NeRF. Then we input the rendered center and right views of the stereo triplet into a deep stereo network, which estimates a disparity map. In this case, we can employ any stereo network, such as the recent Raft stereo architecture. Next, we introduce a NeRF-Supervised loss that consists of two terms. The first one is the triplet photometric loss, which quantifies the photometric discrepancy between the reference image and the warped reference image. This warping is performed using both the left and the right images of the stereo triplet, considering the estimated disparity map aligned with the center image. By comparing the appearance of corresponding pixels in different views, this loss encourages the model to generate consistent and visually coherent stereo reconstructions. Nevertheless, this formulation lacks supervision in occluded regions. To cope with this issue, we compute the final triplet photometric loss, defined as the per pixel minimum between the two pairwise terms. In addition, we incorporate an extra loss term that compares the model's predicted disparities with the rendered disparities generated by NeRF. To ensure the robustness of the training, we employ a filtering mechanism that takes into account the underlying NeRF uncertainty. This mechanism selectively retains the most reliable pixels, discarding those with the higher uncertainty. Finally, our NeRF-supervised training regime combines the photometric and disparity losses with tunable hyperparameters. By optimizing this training regime, we significantly improve the robustness and accuracy of deep stereo networks, resulting in superior depth estimations. In our work, we also conducted several ablation studies to investigate the importance of each component. Specifically, in this slide, we studied the impact of the number of scenes used in the training process, the chosen rendering resolution, and the baseline for generating stereo pairs. We evaluate these factors on well-known benchmarks such as Kitty, Middlebury, and ETH3D to assess their effect on the overall performance. Here we present a comparison of disparity maps obtained by training the Raft stereo network using our NeRF-supervised approach, as opposed to a baseline Raft stereo model trained using a self-supervised photometric loss on binocular stereo pairs, a photometric loss based on perfectly rectified stereo triplets, and the state-of-the-art method stereo from mono. These visualizations allow us to evaluate the effectiveness of our method in enhancing the accuracy and quality of depth estimation compared to the baseline approaches. For more results, dataset, and trained models, please check out our project page. Thank you for your attention.